Okay, welcome to this afternoon's department seminar series. I'm pleased to introduce Ms. Zoe Brooke. She's a second-year student working in my research group. I've known Zoe since this junior year. She's taking 311, and then she worked with me on an undergraduate research project that was supported by the Hillville Board. No, it was a Driftwater Fellowship.
It was through the honors program.
Honors program. And then she's now been working with me looking at adjoint perturbations and adjoint sensitivities related to tropical cyclone intensity change. That'll be our talk today. Zoe hails from Viroqua, Wisconsin, and likes to dance. Yes.
A little bit.
A statistic. Okay, a bit of information. So, turn it over to Zoe, and we look forward to your talk.
Thank you. Yes, so today I'll be talking about the diagnosis of the influence of adjoint-derived perturbations on tropical cyclone intensity, and I'll be focusing on Hurricane Harvey, which are what these radar images are from. I took them as screenshots on my phone. I actually went down to Texas to chase Harvey, so that was me as it was making landfall. I went down with Alex Colton, former flatmate. It was an incredible and just humbling experience to experience that. So if you have any questions about that, talk about that later. But what I'm going to be talking about today is more motivated by the fact that the forecastability of hurricanes is not great for intensity. We've seen continued improvement in track forecast errors. However, we haven't seen that same improvement in intensity, and this is due to a number of reasons. Partially, track, there was a large focus on it that helped gear understandings and improvements in how the steering flow of tropical cyclones. And so now that shift has been focused on intensity, trying to understand more of the mechanisms that are driving intensity, particularly in rapidly intensifying tropical cyclones. And this is being worked on by a number of field campaigns, such as the Tropical Cyclone Intensity Experiment, the Hurricane Forecast Improvement Program, and TPARC 2, which is Intensity Improvement out in the Asian Pacific Basin. And so there's a few ways that we could say reasons why the intensity is lacking, intensity forecasts are lacking. One could say that the models simply aren't capable of resolving the tropical cyclones. The other option is more that the initial conditions, the errors and uncertainties in them are propagating forward and degrading the forecast. And that will be what I'm focusing on today. So the research questions I'm trying to investigate are: what can we learn about tropical cyclone intensity change from adjoint sensitivity analysis? What is the tropical cyclone most sensitive to? And can perturbing the initial state lead to a more rapid deepening? Along with, after we perturb the initial state, how does the evolution of these perturbations, what do they indicate physically? So a brief overview for those who are not in the tropical cyclone world. Tropical cyclones are a warm core cyclone. Favorable conditions for them to form and maintain themselves are warm SSTs, high relative humidity, weak vertical wind shear, and in the low latitudes but slightly away from the equator. Tropical cyclones are also described by two main features. There's primary circulation, which is essentially the swirling motion, horizontal vorticity around the center of circulation. It's described as nearly axisymmetric, and particularly in the mature state, the asymmetries from its axisymmetric state are due to internal gravity waves or Rossby waves. There's also the secondary circulation, which is the in, up, and out Carnot cycle that we have heard of classically, and this is driven by latent heat releases and surface friction, and it results in an inward advection of angular momentum. So the case that I mentioned earlier, I was focusing on, is Hurricane Harvey, which I feel like most people have at least heard of. It was a devastating event in Houston in particular, dumping over 60 inches of rain. However, I'll be focusing on a 36-hour forecast period starting at 12 UTC on the 23rd, and this is as the tropical cyclone is started to organize and is about to undergo rapid intensification, where the larger errors were occurring in the operational forecast. Looking at some of those operational forecasts, we see with the track, there's a pretty good consensus prior to landfall at this time between what was observed and what was forecasted. You do see a slight southwest bias to the tracks, but generally they're in agreement. If you look at the operational intensity forecast, however, you don't see that same agreement. You see a pretty strong deviation after about 20 hours in both the forecasted pressure and maximum sustained wind speed. So again, I'll be focusing on this first 36-hour period after it's beginning to undergo rapid intensification and trying to understand what caused these model deviations. To do this, I'll be using the WRF and its adjoint running at 30 kilometers horizontal resolution with 41 evenly spaced vertical levels. We initialized with quarter-degree GFS final analysis global data, and I'll be running it forward 36 hours and doing a 36-hour adjoint integration on it. This is my model domain. For context, I'll be defining this near environment, which I'll be zooming in to try to get some more detail on what's actually happening with these sensitivities. To just kind of get a quick look at what happened with the storm, we can look at how the central pressure was forecasted. The blue is my WRF simulation. The black is what was observed. We see that they start off at a generally same pressure. The WRF is about 3 hectopascals higher, and then deepen at about the same rate until about 15 hours into the forecast, where the observed started rapidly intensifying and the WRF did not. For context, the HMON and the HWRF also underperformed compared to what was observed, though obviously did slightly better. However, they were both run at higher resolutions with nested inner domains going down to 2 and 3 kilometers for the HMON and HWRF respectively. Looking at the synoptic environment for my simulation, however, first just the top panel is 2-meter temperature and 10-meter winds. On all the fields, the black contour is the sea level pressure. Then looking at the vertical wind shear, average relative humidity, and the potential vorticity. At the initial state, you see that, and it maintains that there's relatively dry relative humidity to the west of the cyclone center. However, the moisture does seem to wrap up as time progresses. You also see it's in a relatively low vertical wind shear. You do see some within the context of the storm due to just faster wind speeds and the anticyclone aloft. And you also see a lowering of PV around the cyclone center. Again, we see that the WRF underperformed compared to what was observed, but it still does resolve a modest tropical cyclone. To get a view of what's happening in the vertical, I'm going to be doing this, taking advantage of the fact that tropical cyclones are axisymmetric and doing an azimuthal average. So just for context, this circle is representing 1,000 kilometers away from the center of the storm, where I'm doing an azimuthal average around it. And what I'm showing here is the azimuthal wind, which is defined as positive is into the board, so the low-level cyclone, and out of the board is the upper-level anticyclone. And then radial wind, where negative is into and positive is out of the cyclone center. We also see the equivalent potential temperature, where there's a minimum equivalent potential temperature and generally moisture near the cyclone center. We do see in the relative humidity that the upper levels are relatively dry, drier than we see in a classic strong tropical cyclone. As these As these fields progress, we see that the azimuthal wind increases, meaning it's becoming a stronger, more vertically stacked cyclone. The anticyclone is also intensifying. We also see a stronger secondary circulation of stronger inflow and outflow from their TC. We also see a moistening of the center of the tropical cyclone, and generally the relative humidity this is at the final forecast hour, it's becoming more moist in the inner core, at least, of the tropical cyclone. There still is some dry air outside of it. But this leads to the question of how can we make this tropical cyclone more intense? And the context we're using is adjoint. So what can we learn about TC intensity change from adjoint sensitivity analysis, and what is a tropical cyclone most sensitive to? So what is an adjoint? So an adjoint-based sensitivity study involves the evaluation of the sensitivity of specific function, which we're calling the response function, of the model output to changes in the model initial conditions. Mathematically, this is described with the gradient dr dx naught. Given this sensitivity gradient, one can compute changes to R attributed to small changes in the initial conditions. And this is described by taking the dot product of that sensitivity gradient with some small changes to the initial state. An adjoint study involves two model integrations. First, your classic nonlinear model propagates your state vector forward in time to some final state, at which point you define your response function, which is some aspect of the forecast you're interested in evaluating. In this case, we're interested in the intensity. You then take the gradient of that response function with respect to the model final state and use that to initialize the adjoint model. Your adjoint is defined as the transpose of the tangent linear approximation to the fully nonlinear model. Yes.
Go to finish your statement all out.
And from your adjoint, you get the sensitivity gradients, which are calculated that are calculated and are indicating how sensitive a certain feature is at the final time with respect to your initial conditions. So in this case, how sensitive is the storm's final intensity to the model initial conditions, such as the zonal meridional wind or temperature, any model state vector? Dan?
But the gradient with respect to the final conditions, what do you mean by that?
So whatever you define your response function, it has to be some modelable variable, and then you take the gradient of it. So you're essentially just taking the gradient of it with respect to any of these variables. Also, we can view wind to see how it changes going into or within the response.
I'm not sure I get your question.
I guess I don't understand what dr/dxf represents.
Right, so it would represent the derivative, so the response function has to be a differentiable function of the model final state. So it has to be a function of the model variables. So if you were to take temperature as your response function, or the average temperature in a box, the gradient of the response function would be 0 everywhere except within the box, where it would be 1 over the number of points in the box. And that would be the gradient.
I see.
So R would be equal to T. Say at a point, if R is temperature at a point, it would be dr dt. It's going to be 0 everywhere except at that point where it's going to be just 1.
Got it.
And so your model will be initialized with 1.
I see, thanks. So it's like I think of it like a norm, almost. Yeah, it's appropriate that you're looking at me like that.
Yeah, I would look at.
I get what you're saying, but I also get why you're looking at me that way.
No, I didn't realize I had that question. I thought I had a poker face.
Oh, yeah, the real poker face.
So I don't play that.
Yeah, okay, so for this specific case, the response function we're using is negative mu bar within the 1004 hectopascal contour, where mu is the perturbation, dry air mass in a column. It's essentially sea level pressure, but it's a model state variable, which means we can actually use it to initialize our adjoint. We also choose negative we choose negative so that positive sensitivities will correspond to an increase in intensity. And then we also choose an area as opposed to a specific point, because if we perturb our model and we allow it to evolve, we want to be able to check whether our perturbations evolved as we prescribe them. So having, in case the center shifts, we can still capture what's happening physically. To get a quick look at what these sensitivities are, I'll describe them more thoroughly second, but just in general, in this case, found that the sensitivities are really maximized within that area I defined as the near environment of Hurricane Harvey. So, and this is at the model initial time, this is true for all times. So we're gonna just zoom into there. So how to interpret these sensitivities? Essentially, if I were to perturb a positive sensitivity with a positive perturbation, I would expect to see a more intense cyclone at the final time. So if I were to make it warmer to the northeast of the cyclone center, I would expect that I would have a more intense cyclone at the final time. Also, not that it's easy to pick here, and I'll show it later, but if I were to make it generally more cyclonic or convergent, I would also expect to see a more intense cyclone at the final time. And this is relatively consistent with what we physically expect. We can also see how these sensitivities evolve forward in time. So these are getting closer to the final forecast hour where we defined a response function, and we see that the sensitivities propagate inward and also become more organized, where you can clearly see that you want to make it more cyclonic and just a warm anomaly at this. And this only goes to its time step prior, so forecast hour 33, where the response function was defined at forecast hour 36. And again, this is consistent. If 3 hours before we defined our response function, if we just add a lot of horizontal vorticity, we would expect a more intense cyclone. Yeah, Maria?
Sorry, I just want to make sure I understand this. But is it that you expect it to, or is that you've actually seen that it does?
So we'd expect it to. Sensitivities, which is why we perturb it, sensitivities are not sufficient to make that dynamical statement. They give us an idea of what we'd expect, but you have to actually perturb the model in order to see whether that is the case.
Can I just add? So the expectation is that if you were to make a perturbation, like at these closer times, like make it warmer where it's reddest, you're going to get a more intense cyclone 3 or 6 hours later. So you can actually calculate what you expect for a given perturbation, what you expect that final change in intensity would be. So it should, if everything's working well, it should.
Is that sensitivity reversible? Like suppose you put in a cold perturbation into it's going to be what happens there.
Yeah, so because the adjoints is defined as linear, we're using a linear assumption. If you would add an equal but opposite negative perturbation, you would expect it to decrease in the same sense if everything evolves perfectly linear, which is not always the case, and will also
That means that it never developed.
Yeah, so you can push things either way, which again I'll show, but you can move them, yeah, either two.
The units are pascals per K.
Yeah, right, because the sensitivities are defined as dr dt, so yes.
So it's not, it's not a temperature scale. That's all.
Yes.
It's a sensitivity, yeah.
We can also see a coincidence of these sensitivity fields. So now overlaying on it is the sensitivity to water vapor. And just kind of flipping back and forth, we can see green indicates positive sensitivity to water vapor, and brown is negative sensitivity to water vapor. So we see positive sensitivity to both water vapor and temperature, indicating kind of a theta E argument to increase the relative humidity in those areas.
What do you mean by theta E argument?
That if you make it, so it's saying that to either make it essentially warmer and moisture in the area to increase the equivalent potential temperature. To the northwest of the storm would likely lead to a more intense cyclone.
Because it increases the humidity.
Yeah.
So can you apply those kinds of diagrams to the thought problem of introducing a local convective cell with a alarm anomaly? And so you can move that around, and if it's in a red spot, it's going to grow and help the stone grow. But if it's not in a red spot, it doesn't do anything. Or if it's in a blue spot and it's too far out, does that detract from the stone grow? Is that a fair application of what you're saying?
I think so, yes. You can perturb a single location, or you can make any kind of perturbation to it. The larger the sensitivity is, just in general, the larger impact you would expect it to have on the final cyclone intensity. And then, yes, whether it corresponds to adding positive, you're warming the area in the case of temperature, it would increase the cyclone intensity. Does that answer?
Is this a moist adjoint or?
Yes, moisture is included. The physics are simplified compared to, they're simplified physics, but they still do have moisture. Well, works. Kind of moving on, we also see that these sensitivities are really confined within the lower levels of the atmosphere. Looking at the 0.975, 0.8, 0.625, and 0.375 eta levels in the atmosphere, and you see there's a pretty rapid decrease of where these sensitivities are, indicating for this case, it's more of the low-level environment that has the strongest influence on the final time intensity.
Does it pick up again if you go a little higher? I don't know what 0.375 is in sigma. Is it something like 300 millibars? Because if you go up higher, people say like mesocalcium triplet, that if you have a weaker inertial stability in the outflow, that it will encourage storm growth. And that sounds like it could be a kind of sensitivity.
Yeah. So jumping to this, in this case, it does not increase. So this is the fraction of the absolute sensitivity at any given level, going from the surface to the top of our model. And at least for temperature, water vapor, and wind, we see that these are all maximized in the lower part of the atmosphere. Pressure is doing something different, and I haven't quite physically figured how to interpret that yet, but at least for the more classic perturbing variables, they are all maximized in the lower atmosphere. We can also take an azimuthal average look at this. So the contours are what I showed before of the azimuthal wind and the radial wind, and the fill now is the sensitivity to the azimuthal and the radial wind, left and right respectively. And so interesting things to note is for the average sensitivity to the azimuthal wind, we see it's maximized just outside that radius of maximal winds. We also see that it's relatively vertically aligned, possibly indicating to make a more horizontal or vertically stacked system. We don't really see much organization as far as the averaged sensitivity to the radial wind. There is, if you've looked at this long enough, two slightly brighter blue spots there indicating making a slightly stronger inflow, but the sensitivities look stronger to the azimuthal sense. You can also see those evolve and see how they change in time. You, again, similar to the horizontal view, see these sensitivities, particularly in the azimuthal, sensitivity to the azimuthal wind, propagate inward. You also see that they stay relatively confined to the surface in the azimuthal wind. I'm not sure if this is a physical response. There are some adjustments to the adjoint. I don't know how to physically interpret making it more inward throughout the entire area. So we'll not focus on that. However, we will focus on, as Maria pointed out, I think it was Maria pointed out earlier, can you actually say that making it more cyclonic, say 3 hours prior to the forecast, is going to make it more intense? you can't say that just based on the sensitivities, and sensitivities alone are not sufficient to prescribe dynamical significance, so we perturb our model. And how we're doing it is through optimal perturbations, and what I mean by optimal is we seek those perturbations with the smallest initial energy that produce prescribed change at the final forecast time. The prescribed change that I'm making is a 1 hectopascal decrease in pressure over the response function domain, which is again that contour I showed before. The perturbations are calculated based on the prescribed change and the sensitivities gradients at the initial time. For this case, the perturbation values, the maximum is 11 and 3.7 meters per second for U and V wind, which are too large, but less than 2% of the perturbations are greater than 1 meter per second. Those are like 5 grid points. And I've also had them removed from some of the simulations, and it doesn't really impact how the perturbations evolve, so we're just gonna ignore that and move forward to see how these perturbations changed our forecast. Looking again at how the central pressure, and now looking at the control versus the perturbed run, we do see in fact that we get exactly this 1 hectopascal decrease in the final central pressure. However, this alone is not sufficient to say that it worked. That's kind of a happy accident. A better way to quantify whether or not the perturbations evolve linearly is by looking at the difference in your response functions. So this is the difference in mu at the final forecast hour. Things to note, the sensitivities are pretty well confined within that 1004 hectopascal contour. And they're also predominantly negative, indicating that what we prescribed evolved pretty closely to how we wanted it to.
I think you said sensitivity to
Yeah,
perturbation, right?
Wasn't sure. But yeah, this is the perturbed minus the control simulation.
And the DR of 1 hectopascal is the average inside your
Yeah.
area? Okay.
And that's again what I mentioned. We have a larger, we have an area as opposed to a point. So we're averaging over this entire kind of domain, response function domain, to account for any shifts that may have occurred in the track.
What happened to the pressure? Sorry. LVUR.
So the minimum central pressure.
Oh, that's not
yeah.
the average over the domain.
No,
Yeah,
that's just the minimum central pressure.
Okay, that's no problem.
To see how the average, or so essentially to see how linearly these responses, these evolved, we can do a linearity test. So essentially to determine how accurately the prescribed change compares with the measurable change from the difference of the control and the perturbed simulation, we test the linearity, where high percent linearity corresponds to perturbations that are made to the simulation, where perturbations that are made change as prescribed. And thus, the assumption we use for the adjoint's trajectory is valid. So linearity is impacted by a variety of features. Diabatic processes and moisture are some main ones. Also simulation length, model resolution, and perturbation size all impact the linearity. So I've tested a number of cases, both trying to decrease the intensity and increase the intensity. I also perturbed a number of different variables. The big thing to take from here is the larger the prescribed changes, the less linear the response is. Additionally, the more thermodynamic variables, so if you add temperature and moisture, pressure to the perturbations, the less linear the response is. Additionally, there seems to be a more linear response when you're trying to decrease this storm than you're trying to increase it. And this is just for this case. This varies case by case.
Is it possible that it's somehow vaguely related, that departure, to gravity wave radiation? I know that sounds like a leap of imagination, but in the adjustment process, maybe that somehow explains the difference. I don't know.
I don't know.
Well, that's an interesting question. I think, though, by 36 hours, any of the gravity waves that were put in at the initial time would have probably radiated out of the domain.
so that they probably would be contributing significantly to it. I was just trying to think of why it would damp out instead of, you impose this specific thing, but it doesn't turn out quite as strong.
Yeah. So, I know that I haven't done it, but for some other cases, it's not always the case that weakening the storm at least results in a more linear response. If that's why you're thinking. Yeah. I haven't really concluded the exact reasons why there's a larger deviation for increasing rather than decreasing. Right?
Yeah, is this using cumulus parameterization,
Yes.
35 kilometer?
Yeah.
So cumulus parameterization doesn't respond to inertial stability. So I'm like,
Oh.
So then you're saying then that
you wouldn't see
capture
it.
wouldn't see,
You wouldn't see the response to outflow resistance.
Okay.
Why not? Why do you say cumulus parameterization won't respond?
Because it doesn't have any dynamics for outflow. It doesn't have, it's just looking at the thermodynamic structure for cumulus, and it's kind of, I don't know, which one are you using?
I don't know that off the top of my head.
it's Cambridge for the month, so.
That sounds kind of familiar. I can get back to you on that. I don't remember off the top of my head.
They don't conserve momentum or anything like that, so they couldn't really feel an inertial resistance.
Tom?
I think I'm following everything, so I may be off base, but this final step here led to this diagram, were there actual runs that were perturbed, and then you had a perturbed run and a non-perturbed run, and you look at the difference?
Yes, so these are all these dots here correspond to a perturbed run. So I made prescribed changes in various sizes, and I looked at I haven't done an in-depth analysis on all these cases, but I was curious to just kind of see the trend if you make larger or smaller perturbations to the initial state.
So a dot diagram like this sort of is a macro description of
Yes.
what happened.
Mhm.
Did you ever just, for example, make plots in the vertical cross-section of the perturbation temperature field as a function of time to see what the heck is going on to explain how these dots end up where they do?
I haven't done that with
You know, some
temperature.
physics. in other words.
Yeah. I do have the progression of the sea level pressure for 5 of these cases. So the control run decreasing it by 1 hectopascal and decreasing it by 2 hectopascals, as well as increasing the intensity by 1 and 2 hectopascals. So trying to see if I can nudge it both ways. And you see that lesser response in the increased intensity here. So I've looked at a little bit of the response, but I have not looked at as wide of a diagram of all those.
So I think that's the next figures you're showing.
Yeah,
really.
I will show some, not, yeah. So to kind of conclude on this first portion of it, quicker. So kind of going back to some of the research questions I asked, what can we learn about TC intensity change from adjoint sensitivity analysis? By using mu as a proxy for intensity, we found that modest resolutions and small prescribed changes, optimal perturbations evolve within the linearity constraints of the adjoint model. And then what is the tropical cyclone most intensity most sensitive to? In this case, we found that the sensitivities are concentrated in the near environment of Hurricane Harvey, and the initial diagnostics show that the sensitivities are concentrated in the lowest levels for temperature, water vapor, and the winds. And this is consistent with previous studies. Doyle et al. 2012 is another adjoint study, and then Brown and Haycomb is an ensemble sensitivity analysis, both focusing on tropical cyclone intensity. And then the perturbations to the initial state lead to a more rapid deepening? Yes. The prescribed optimal perturbations did act to increase the intensity at a slightly more rapid rate. So then, as John was kind of alluding to, what does the evolution of these perturbations indicate about the physical processes? So to kind of motivate that, I was interested, as I mentioned before, going back to the sensitivity field and the perturbations from it to the full wind. You can't really see it, but these perturbations are generally cyclonic and convergent. And one way to see this is to partition the field into its azimuthal and its radial components. And what I mean by that is if you have winds around your cyclone center, through some simple geometric arguments, you can partition it into two components of flow and then define that as the azimuthal and the radial circulation. So going back to that full wind perturbation case, I partitioned it into its azimuthal components and its radial wind components. And what you see then is, again, it's all swirling around the storm and going into, and this is just one level, but I partitioned it throughout the entire atmosphere in model domain, and I allowed that to be forecasted, or to integrate those three different cases forward in time to see how the perturbation fields evolve. Things to note is the full perturbation wind field and the azimuthal perturbation wind field evolve relatively similar, where you see that the difference in mu, which is what this is showing, is about the same, has about the same spatial organization as well as intensity. The radial wind doesn't really have much of a spatial structure to it. Also, the magnitude of it is smaller. I should have noted before, the prescribed change was greater to the azimuthal wind than the radial wind. However, you still don't see the same kind of structure evolve. You can also take a look at the azimuthal difference. So this is how I made these azimuthal averages, as I did the azimuthal average of the non-perturbed case, storm-centered around the non-perturbed case. I then took the storm-centered average around each of these three cases and took the difference of that. So these are storm-centered differences. And then again, for the fully perturbed wind, just perturbing the azimuthal wind and just perturbing the radial wind. And then again,
Oh, that's just on that. That's running the full nonlinear model?
yes.
Yeah.
These are, the perturbations have been put back into the fully nonlinear model, propagated forward the initial time, and this is the final forecast time. And what you can see here, I'm interested in the response. You can see that all of them are, well, the perturbations are predominantly made to the lowest levels. As you can see here, this shift, the control is in black and perturbed is in gray. You can see that these shifts are concentrated in the lower part of the atmosphere. The change is greatest in the inner part of the cyclone and in the upper levels of the atmosphere, indicating that it's the perturbations you're making are making a more vertically stacked or more equivalent barotropic environment, and also making a more stronger cyclonic circulation at the final forecast time. Interestingly enough, you don't really see the actual center of the storm increasing as great as you do as above. You also see a slight increase in the anticyclone above, and there's an interesting shift between the just perturbing the radial component. The anticyclone shifts slightly inward, whereas the azimuthal perturbations and the full wind perturbations are just expanded outward slightly. That's correct?
Is that the actual top you mount at 16 kilometers? Is it?
No.
Yeah.
That's something I can also see how much more it goes up, but yeah, it is not the top of the model. Also, just looking at the perturbations to the radial wind, or looking at the differences in the radial wind, it's a little bit less of a clear indication of what's happening. You still see the maximum differences occurring in more of the outflow layer, but it's not as clear of a depiction of what's happening. You do see a slightly stronger inflow also at the surface that evolves, but it's not as clear as what's occurring.
What is the outer grid here? I mean, is it a
Um,
big, like a hemispheric grid or something like that?
The entire domain is, yeah, pretty much the northern hemisphere.
Yeah, okay.
Not quite the northern hemisphere. It's large, and this is relatively far away from the boundaries. If it's a boundaries
Sure.
question, boundary
Yeah, I'm
conditions
just
kind of imposing
wondering
on the
about that,
storm. So yeah, we specified the domain so that Harvey would be relatively in the center of it, as far away from the boundaries as possible. And this is just a small snapshot inside of it,
So
about
it's
1,000 kilometers.
It's at least 1,500 to 2,000 kilometers from the boundaries.
Yeah. And so, just kind of wrapping up, this is also this is showing the fraction of kinetic energy per level for the three cases, color-coded, and then I'm finding the fraction of kinetic energy for the azimuthal and the radial component of each case, essentially to see where we're putting energy in at the initial time, so where are we putting the perturbations in at the initial time, and where are we seeing them resulting in the final time with the greatest changes. And that corresponds to the darkest colors here. These 4 lines correspond to the initial forecast hour. These lighter lines correspond to the final forecast hour. Essentially what we're seeing is the perturbations are made in the mostly below 2 kilometers at the final forecast hour, and at the final forecast hour, we see that these perturbations are maximized at about 14 kilometers. So we see this shift up, even though we're perturbing the lower part of the atmosphere, we're resulting in a stronger kind of upper air dynamics of outflow and making a vertically stacked system. And just to kind of go back to this linearity assumption that we talked about earlier, for the full azimuthal and the radially perturbed cases, we see there is a larger perturbation to the azimuthal than the radial wind. Additionally, we see that the azimuthal wind evolve a lot more linearly than the radial or the full wind, which is something interesting, and I'm curious why exactly that is. And you can see that also resulting in how the sea level pressure drops for the 3 cases. The 4th line on here is after I partitioned the winds, I combined them back together to see if I was doing it correctly. It resulted in, I'm not sure why, but a small difference, which you can see where there's a slight deviation between the full wind and the recombined wind, but they generally are consistent with each other. So again, going back to research questions, what does the evolved perturbations indicate about the physical processes? Well, we can see that the calculated optimal perturbations are concentrated in the lower part of the atmosphere, but evolve to change the wind in the outflow level. Additionally, optimal perturbations in the full perturbed case are predominantly partitioned into the azimuthal components of the wind. Additionally, as all the perturbations evolve, there's no suggestion for a preference to evolve into the azimuthal or the radial component, which is something I didn't show as much, but going through the size of the perturbations seems to be that way. Additionally, the evolved winds create a more vertically stacked system. Those are kind of the summaries again. Just for the sake of time, let's just go to some future work. So I'm interested in doing a more thorough investigation of how perturbing the partition of the winds with other model variables, so perturbing the winds and also perturbing temperature or moisture fields, seeing how the combination of those evolve, seeing if there's anything dynamical in physical processes of how these perturbations evolve. Additionally, running the tangent linear model for this case, as that's an important step to check whether the adjoint sensitivities and the linear perturbations are actually evolving linearly. I'm also interested in looking at other case studies, both for similar and different environmental conditions. Harvey was pretty isolated from any larger scale synoptic flow, so it might be more internally driven than some other cases, so I'm interested in looking at that. Additionally, exploring the partition of other fields, such as seeing if partitioning the temperature into its mean and perturbation state, how that evolves, and also using this iterative technique that Fred Hoover and Alec Goldstein developed to help test this linearity or loosen the linearity constraints, where you're going back and making small changes multiple times to see if that can help continue to nudge and increase the intensity of the storm. And then also just seeing how defining the response function influences the sensitivities. And with that, I'll take any questions.
One of the big forecast problems in Gulf storms is always the sea surface temperature. I suppose you're getting at that by looking at the sensitivity to low-level temperatures.
Yeah.
But you're not doing it directly, but you could.
Yeah. I don't know in the WRF if we explicitly can, but yes, the lowest level temperatures, like eta level 0, would be similar to sea surface temperatures.
But although the sea surface temperatures are most affected in the core of the storm rather than on the outside.
Yeah. Yeah. And unfortunately, this is not a coupled model, so the sea surface temperatures do remain fixed also throughout the entire model integration. So that there's a limitation there. Yeah.
I think also the sea surface temperature might be a little bit tricky to deal with because it's not explicitly a model variable. I don't know if it goes under a boundary condition that you might be able to get a sensitivity to the bottom boundary. But
I think the ARW isn't that coupled with the sea surface?
I don't think the adjoint certainly has it coupled. So
Well, I don't, yeah.
and there's an SST, an underlying SST, but how that actually gets in, I don't believe.
And the way the Gulf is important is the depth of the ocean heat
Right.
content, because usually you have such a skin-deep thermocline that it mixes out, and that limits the strength of the storm. So
Right.
the deep thermocline is what really makes them strong in the Gulf.
Right, and that's an aspect that can't be at least directly explored with the tools that we have at this point.
So kind of along similar lines, when I see all these perturbations mattering most in the lowest levels, it kind of triggers to me that your surface layer or boundary layer parameterization might be playing a role, especially if you're increasing the winds in any way, shape, or form. So have you thought about looking directly at like things like surface lake heat fluxes or the way that perturbations are changing those things?
Yeah, I started looking around at those variables, but I haven't done a deep dive into what those are physically doing and indicating yet.
Were you expecting to see outflow sensitivity? I mean, in this case, it seems like the outflow is a consequence of what's happening near the surface.
Yeah. Yeah, so
But I guess, Greg has some ideas about how the outflow influences.
yeah, in this case, and the sensitivities don't have much of a strong signal about the outflow and what it's doing. In other cases, the first kind of way I was approaching this was doing near real time, so I was in the
So you did more cases.
yeah, in the West Pacific Basin, so I was Northwest Pacific Basin, so I was looking at a lot of these constantly, and it depends on the storm. Some of them do have a lot larger sensitivities aloft, especially if they're interacting like a jet feature, and how that is definitely influencing the outflow. But in this particular case, it didn't just really solve that.
I think my question's related. I was thinking about it just as you were beginning to say yours, Larissa, so I don't know if I got the answer to mine already. But what if you decided instead of minus mu to use, some kinetic energy measure at 14 kilometers as your parameter, and then do all of your gradients based on that? What might you find underneath that are other, they're not responses, but they're associated physical processes? I guess in some way you should see the same thing, but in reverse. But you probably won't, and it'd be interesting what the differences are.
Yeah, that's an interesting idea.
So response function is in the outflow layer.
Yeah, right. Expressly looking for things that are occurring in the outflow layer and then see what they're associated with. And then maybe is there a way, I don't even have a concept of how you would do this, but you mentioned the larger scale environment away from the storm and surrounding it that might have a big impact on the outflow layer, and that's consistent with a lot of theories and things that Greg's talking about. Is there a way to make a sensitivity of some forecast aspect of the larger scale environment? I don't know which one it would be, but something like the inertial stability, something like the negative vorticity, something like that.
Probably.
Because you have like 20 millibars here that you can't account for, and I wonder
Yeah.
if you'd get some of that back if you concentrated on another forecast aspect.
Yeah, that's an interesting thought. I can't think of something off the top of my head. But that probably could be conceived, yeah.
It does seem like you're sort of suggesting a diesel truck model where you put the accelerator down low and you see the stuff coming up that the smoke stick.
Yeah, that's right.
But seriously, so I didn't know. I was unaware of this problem of trying to track the sea level, the minimum central pressure. So we've been trying to simulate tropical cyclones with Greg's model, and sometimes even if you initialize at 2.5 degrees, you get it tracking exactly correctly. It's astonishing. And other times you use higher resolution initialization, higher resolution runs, and it doesn't necessarily do better. And a couple of things come to mind is it possible, I guess this is a question, is it possible, do you think that you can say that the hurricane can be represented fairly with reasonable fidelity even if the central pressure is kind of messing with it? Is that a fair thing to think about? Or is it to have it 220 hectopascals too high of a central pressure damaging to the whole argument? Because some of the reviewers kind of go in that direction.
Yeah. So I have done forecasts of higher resolution, not high enough to be cloud resolving, but I've gone down to 10 kilometers, and so I've done 10 and 15 kilometer runs to see is this actually, a feasible thing, which the 10 kilometer run does actually get in the range of the HMON, which is kind of promising. And then I also, these are the sensitivities, which I showed a ton of the low level sensitivity to temperature for the three. And so I still, the general consensus between what the sensitivities are showing are consistent within even like going up to higher resolutions. However, perturbing the model based on the higher resolution sensitivities, the linearity just kind of goes out the window, which is one of the reasons why we stuck to 30 kilometers, which is not really sufficient for resolving the hurricane, but it's still possibly give you some physical insights of the larger scale.
It seems like it's challenging for people to actually estimate just the so-called observed minimum pressure, that there's different techniques and that there's a fair bit of uncertainty in that. Is that an impression to you? I'm not an expert, but it just sort of seems like that is the case.
Well, historically, I think, Dan might know more about this than I do, but historically, I think that might be the case, but recently, we've got increased.
How do you get pressure from that?
Drops.
And it has to get right in there. right. I'll believe that. That's not always the case, though. If it drops out,
I did the southern hemisphere's relations with your analysis, and so what did you see in the difference in your sea level pressures? Because for our work, we have a lot of problems with sea level pressures in the southern hemisphere. Off a fair bit from what perhaps was observed, but is observed in the southern hemisphere. So have you done any in the southern hemisphere?
I have not. Interesting. I did run into an interesting issue where the minimum in mu is different from where the minimum in sea level pressure is in some cases. I'm not 100% sure the reason why, but that was something interesting. When I was defining my circulation center to perturb them around, I ran into that issue where it sometimes wasn't, you could see where the circulation center was and it didn't correspond to where the actual minimum sea level pressure was. But I ran into that more, especially when it was in the initial state, when it wasn't as well developed, it wasn't as difficult to see. They were more aligned when it was a stronger cyclone.
Any other questions? Thank you.